So the first rule we'll derive is that of a line. So if we look at the line bx plus c, we actually already know that the slope of this line is b. The c is just our y-intercept and has nothing to do. So when we compute this, we should get that the derivative is b. That should fit in with your intuition. Which of course means that the differential of a line is simply b dx, which is the form that we'll derive. Now remember that we have that du is equal to the derivative of u dx. And u prime itself, in general for any function, if it exists, is the standard part of the change in u with respect to the change in x. And so this is our underlying piece of machinery that will be sitting behind every single one of the proofs. This idea that the differential of u is u prime dx, where u prime is the standard part of du divided by dx. So every time we prove anything, this is what we'll always come back to, because this is our solid definition. So back to this. We need to compute the change in u, and we need to compute the change in x. So we have that u, in this case, is equal to bx plus c. So if delta x is an infinitesimal, then the change in u is going to be b times x plus delta x plus c minus regular u, so that's bx plus c. And we see what we get here. This bx and that negative bx will cancel. This b and that delta x has nothing to cancel with. The c and that c will cancel. So the change in u is simply b delta x. So then the standard part of change in u over change in x is the standard part of b delta x over delta x. They cancel, and so this is just b, our real number b. And so we get from our rule then that the differential of bx plus c, remember this is our u prime, this is technically our derivative. Let me write up here the derivative of bx plus c dx. So then we say the differential of bx plus c is exactly b dx. All right, so there's a fact for any line, any slope b, that the differential of that line is b dx. This will be our building block to prove almost half of the other theorems we have in here. So let's take a look at the next extension or the next theorem that follows, and that's going to be our sum rule. So here we have two functions. We don't know what they are, but there's some function u that is dependent on x and some other function v that's also dependent on x. So these are the dependent variables. My independent variable is x. They're just some arbitrary functions. And the rule says that if I add them and take their derivative, that it is just the sum of their derivatives. Or in differential form, the differential of u plus v is the sum of their differentials. And so this is, again, going to be straightforward from our definition. The change in u plus v, remember they're functions of x, so their change is simply u of x plus delta x plus v of x plus delta x minus u of x plus v of x. And grouping these together, this is u of x plus delta x minus u of x plus v of x plus delta x minus v of x. And notice this is just my change in u. And this is my change in v. So when I look at the standard part of the change in u plus v with respect to x, this is the standard part from what we just calculated of change in u plus change in v divided by change in x, which is the standard part, just breaking up the fraction. So now we're just doing symbol manipulation here, plus the change in v over the change in x. And then standard parts distribute across addition. So this is the standard part of change in u over change in x plus the standard part of change in v over change in x, which is the derivative of u with respect to x plus the derivative of v with respect to x. So now we can formally write that the differential of u plus v with respect to x, which is what we just calculated here using this standard part, is equal to du dx plus dv dx, or in differential form, d of u plus v is equal to du plus dx. And notice going from here to here is just a matter of multiplying through by this, the denominator dx. Right? I've got a dx in all of these terms. So if I multiplied the right-hand side by dx, I'd get canceling, and I multiply this side by dx, I also get canceling. Right? Cancel, 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 which gives me this nice differential form. So they're, hopefully see that they're closely related. So now we know how to deal with a line. We know how to deal with, if I add two functions together and I happen to know their derivatives. And so from there, well, we need one more piece before we can get to how to deal with polynomials in general. And the constant rule says if I've got any function I'm interested in, any function u that depends on x, and I multiply it by some other constant, that I can simply factor that constant out, and so it'll be the constant times the differential of u. And this is going to be a very handy rule. When I get in differential form, I can factor, you can think of this as factoring the constant out, and they fall out of the differential. So again, I have to, just like in all the other examples, I have to look at the change in Cu, which is constant times u of x plus delta x minus constant times u of x. Now I've got a constant in both the pieces, so I could factor it out. So this is constant times u of x plus delta x minus u of x. And this term right there is just delta u. So I can say that this whole thing is just equal to constant delta u. So then the derivative of cu with respect to x, by definition, is the standard part of the change in cu with respect to the change in x, which from our algebra up here is equal to the standard part of a constant times change in u over change in x. And again, our rules about constants, that this can factor out of the standard part, so this is equal to the standard part, or c, sorry, times the standard part of change in u over change in x. And standard part of change in u, change in x is just, so that's the constant times du dx. So we just showed that just like we did, that's up here, we said we were going to prove it, we did it. The differential of a constant times a function with respect to x is just the constant times the derivative of that function, or in differential form, dcu is equal to c du. So now we know how to deal with constants in front of any function. So that leads us up to asking, well, what happens when we multiply two functions together? So we know how to add. We know if we multiply by a constant what we get, but what if we multiplied by two different functions?